We now consider the dynamics of combined translation and rotation using the example of a solid sphere rotating down an inclined plane, radius r, no slipping or skidding. Its acceleration will be its angular acceleration times the radius. That's a kinematic expression there. But now this analysis will be really important. From my experience, it's one that is easily confused, especially in terms of how friction acts in such a case and what its role is. So make sure you understand this and can replicate it on your own, because you'll be expected to on quizzes and tests, and maybe even in other aspects of life that you don't know about, but we'll see. In any case, a free body. So we have the sphere, positive sense of rotation, and gravity acts straight down, right through the center of mass. So keep in mind, first of all, that this gravity acting on this, since the line of action is through the center of mass, it can't spin up this ball. Gravity has no ability to spin it up because it's acting right from the center of mass. So if you're thinking that gravity is what spins the ball up, think again. Well, that's not the only real force acting on this sphere. Remember I said there's no slipping or skidding. The normal force, just ideally at least, acts normal. It always acts normal, in other words, perpendicular to the surface. We'll see shortly that the surface can actually be deformed by the pressure against the surface, but for now, we have the normal, perpendicular to that inclined plane, and friction acting up this ramp. It's probably not too surprising to you. You think, oh yeah, friction always acts opposite the direction of motion. The motion is down the ramp, friction is up the ramp. But be careful. Keep in mind that there's no slipping or skidding. So one of the biggest fallacies, one of the biggest common errors that people tend to make is thinking that this friction is doing work. It's doing work on that's non-conservative, that is, translated into heat. Well, that's true if it's sliding, like you're used to. Block sliding down the ramp, friction is also acting upward. But this is not the same thing. This is actually the force acting along the edge through the center of mass that causes the sphere to spin up, to have the angular acceleration. That is the force that provides the torque to spin up the ball, not mg. Granted, if mg is gone, then friction doesn't even arise in this situation and can't do the job. But it is actually friction doing the job, not gravity. Okay, did I emphasize that enough? Now, gravity has a component parallel, mg sine of theta, or phi, and then the normal, which would be mg cosine of phi. So let's break that up into its components, wiggle out mg, and recognize now that we can sum of the forces in the y is 0, but we don't care about that because we're not worried in this basic analysis about the amount of normal force. So let's see, that's going to be, friction. We're going to have mg cosine of theta, or phi, and that's the force times distance is the work done by friction. No, it has nothing to do with work done by friction. So we're not, the only thing we're interested in is that the normal force is sufficient so that the frictional force can do the job that it needs to do, which we're going to see what that is. Well, we already know. It's to spin it up, and it has to do it without slipping or skidding. Moment of inertia, 2/5 mr squared. Sum of the forces in the x, mg sine of phi, down the ramp, that's from gravity, minus friction. So those combined forces give us ma. Sum of the torques, F times R, friction times radius, which is I alpha, which is I A over R. So now we have the alpha converted to regular acceleration. So this is 2/5 mr squared times alpha, which is A cm over R, equals 2/5 MRA. So one of the R's went away here. All right. Well, that's equal to FR. The R's go away, and so we have friction is 2/5 A. And what are we going to do with this for friction? How does it affect the motion of the ball down the ramp. Well, that's readily observable, and let's figure out what that is. So, friction from the first equation, m times g sine of phi minus a. And if we combine that with the 2/5 ma, m's go away. And so now we have 2/5 a from over here. And we have 5/5 a, so we're bringing that over, so it's plus 5/5 a equals g sine of phi. Thus, ACM, we have, well, obviously 2/5 plus 5/5 is 7/5 is g sine of phi, so a is 5/7 g sine of phi. So the friction is m times g sine of phi minus 5/7 g sine of phi. So we have basically 7/7 minus 5/7 is 2/7 g sine of phi. So the friction then is 2/7 mg sine of phi. Very interesting. You can see, even though this is acceleration and force, F is ma, so there's the m, but otherwise this g sine of phi, 5/7 g sine of phi, and the 2/7 g sine of phi arises from the frictional force. Notice 2/7 of the effect on acceleration are from friction. And that again has to do with the fact that the moment of inertia for a solid sphere is 2/5. So we have, ultimately we have 7 parts. 5 of the 7 parts are wrapped up in the translational acceleration. Friction, which arises from the effort needed to spin up the solid sphere, accounts for 2/7 of that acceleration. Kind of takes that away. So hopefully that makes a little sense. You can see those proportions again. Now, what μs is required to prevent slipping? So we've just considered that so far. There is enough μs so it doesn't slip. Well, what's the minimum that it can be? Well, let's go ahead and write the definition, friction over normal. And the friction needed is the friction that we had in this problem. We have to deliver this much friction. If the coefficient of friction is too small, it won't be enough and it'll slide. So it's 2/7 mg sine of phi over mg cosine of phi. M's and g's go away. And there is the minimum coefficient of friction needed, 2/7 tangent of phi. If there is no friction, of course, then ACM is just 7/7 g sine of phi. And that is a good introduction to the way in which you analyze a sphere or some other object rolling down an inclined plane. Let's consider rolling friction in a little more detail. Usually we don't have to be concerned about this, but if for no other reason, it should be satisfying to your natural intellectual curiosity. And I alluded to this before, that we don't usually have ideal surfaces. An ideal surface, which is usually what we consider, perfectly solid ramp with a sphere on it. It's rotating at omega, going down this ramp. The normal force, normal of the surface, that line of action goes through the center of mass of the sphere. Friction acts straight up the ramp. The normal force exerts no torque on the sphere because it's going through the center of mass. So again, that force, which is a real force, as gravity is a real force, neither cause any rotational acceleration. They produce no torque. Now on a real surface, the ball or the sphere is going to indent the surface just a little bit. So it's kind of significantly exaggerated here, but it mushes it in a little bit. Now you can imagine that, there's just not one point of contact, but a region of contact. And it's at different angles and different forces along there. Well, the average frictional force is still going to be pointing up the ramp. That's the force that provides the torque to spin this thing up normally. So the average friction force is like this, but let's now consider what the normal force looks like. You could probably surmise that that it might be a little more complicated. I mean, we have little miniature normals all along here, right? But the way this works is that the average normal force doesn't go right through the center of mass. It might look something like what I drew here, so that there's actually a radius arm. The normal force the line of action of the normal force does not go through the center of mass. So there is a torque with respect to the center of mass as a result of that. And that torque is equal to that radius times the average normal force. And it's in the counterclockwise sense. So going down like a soft inclined plane, you will notice that going down a soft material, it will not accelerate as rapidly. And the reason is because the normal force is also putting a torque that's opposite the direction of rotation and angular acceleration to reduce that angular acceleration. Let's consider the interesting situation of a sphere going up an inclined plane. And here is the sphere coming in at some velocity to the center of mass and some omega. And then as it goes up the ramp, we have a reduction. It's slowing down as it goes up the ramp. So the question of the moment is, what is the direction of friction acting on this sphere as it goes up the ramp? So I'll let you think about that for a little bit. So have you come to a conclusion? I haven't left you yet. I'm anticipating the amount of time you'll think about this. What's the direction of friction as it goes up the ramp? Now I'm going to assume that you're thinking, well, here's at least a way to think about it. The sphere is moving up the ramp, and friction always acts opposite the direction of motion, right? So it'd be down the ramp. To bolster that conclusion, you might say, well, it's slowing down. So the real force causing it to slow down would be friction acting down the ramp to reduce the velocity of the center of mass. All that seems very reasonable. But let's consider the following. As a ball rolls up the ramp, the velocity of the center of mass goes down. So I already mentioned that. So you're thinking, aha, see, the friction must be acting down the ramp because the velocity of the center of mass goes down. However, that means omega goes down as well. See omega? It's not spinning as fast as it was. Therefore, rotational inertia, I shouldn't say therefore, but rotational inertia will resist a change in omega, right? So omega doesn't want to go down. Omega wants to keep going at the same rate it was. It wants to keep spinning at the same speed. In order for that not to happen, we already know that gravity cannot produce a torque about the center of mass. For omega to get less, friction must apply a torque to decrease the omega. The only way for this omega can go down is for an external torque to be acting in a clockwise sense around this thing so that omega is reduced. And for that to happen, you know the direction of the tangential friction force. It's got to be like this. That's the only way for omega to go down. So therefore, you just gotta believe in friction. Now, if that all confuses you a little bit, let me just kind of consider another scenario here. So we're going to take this sphere, raise it up a little bit, and spin it. No, that's the wrong way. Let's spin it the way it's supposed to be going here. We're spinning it counterclockwise, and we're going to spin it up like a motor. Really get it spinning. So spinning like crazy, and then we're going to lower it down onto the ramp and let it go. So spinning like mad. It's going to be slipping on the ramp. But don't you agree that it'd probably just accelerate up the ramp if you just dropped it down? Now, mg sine of theta is doing everything it can to slow it down this way, going down the ramp, but something must be giving an up the ramp force that's greater than mg sine of theta, and that would be this friction. So the friction force acting on the sphere, it'd be bigger than this one is, would be greater than mg sine of theta, and away it would accelerate. It would accelerate up the ramp while the angular velocity is getting less and less. And that's a little more complex because it's slipping, but nevertheless, the friction force in all those cases have to be up the ramp. Now let's say it gets to as high as it's going to go. Here it is. It comes to rest, and then it starts rolling back down. Did the friction force just change? Well, no. the friction force is still acting up the ramp to continue to angularly accelerate it clockwise. So mg sine of theta will still relentlessly try and accelerate it at g sine of phi, but this friction force acting in the opposite direction will reduce that acceleration. So the friction force is always acting up the ramp in such a scenario.